So today our topic is geomorphology and wetlands in Minnesota, and our speaker is Dr. Daniel Dejoode. He's an ecologist with 25 years of natural science experience in wetlands, plant ecology, forest ecology, endangered species, and environmental review. He has completed numerous wetland and ecological projects in the Midwest and Great Lakes region for a variety of projects, such as highways, pipelines, mines, and utilities. He's an experience in applying botanical and ecological science to a wide variety of impact analyses, including wetland delineation and investigations of rare natural communities such as calcareous fens and rock outcrops, greenhouse gas emissions from land use conversion, wild rice distribution, and ecological impacts of oil spills and land development. He has a BS in agronomy and an MS in botany from Iowa State University and a PhD in ecology and evolutionary biology from the University of Michigan. He is currently a senior biologist and project manager with SWCA Environmental Consultants. So take it away.
Great. Thank you, Casey. Welcome, everybody. Thanks for joining me today. Casey, is there a chat function for questions?
Yes, there is.
Will you be monitoring that during the talk?
I can do that. Yep, I can do that.
You're welcome to interrupt me if somebody has a question you want to put it in the chat, or if you want to unmute and interrupt me, that's okay. I don't mind interruptions for questions. Casey, I appreciate if you would monitor the chat and let me know if there's any questions during, or we can wait till the end for questions. Okay. Well, I'm happy to be here and sharing today. I'm trying to share my screen here. I've been a member of the WPA for many years as I've been here in Minnesota, and it's a great group and a great forum for sharing information. I'm going to talk today about geomorphology and wetlands in Minnesota. And this is a topic that's of interest to me because it's something that I've learned about over the years, and I think it's important. It's helpful to understand problem areas, understand the occurrence of wetlands and natural areas and ecosystems, and it helps me understand and problem solve sometimes when I'm doing a project, say a delineation or a wetland impact assessment on a site, and there's problems I can't figure out, and a lot of times they're related to understanding the geomorphology. Today I'm going to give you an introduction. I'm going to talk about glacial history. I'm going to talk about Minnesota landforms, and I say Minnesota landforms 101 because it's going to be kind of an introduction to glacial landforms and other landforms that are important. And then I'm going to tell you about some applications of this information and give you some examples from some of my work that where geomorphology has been important or been helpful to understanding a project or a problem that I've faced. My introduction to geomorphology started when I went to graduate school at the University of Michigan. I had this great professor, Bert Barnes, and this picture here shows Bert Barnes in a soil pit in a forest. And he taught forest ecology, and I took a couple classes of forest ecology with him, and they're among the best classes I ever took in college. In the first semester of forest ecology, we had a 6-hour lab once a week. And about half the time we spent doing activities that what I expected to do. We were measuring trees, we were counting trees and saplings and seedlings to understand the forest. But the other half of the class we spent in soil pits to look at the soils, to understand what the soils were, to understand the permeability, to understand the nutrient richness of a site, and to understand the glacial landforms and glacial history, and to synthesize or integrate that with the forest, the biology data on the trees to understand an overall more holistic approach to understanding the forest. And I put this quote up here: you got to know the territory. Some of you may be familiar with The Music Man. The musical The Music Man is showing in the Twin Cities right now at the Chanhassen Dinner Theater. Well, Dr. Barnes would come into one of the early classes and he would sing the opening song from The Music Man. And it has a line about you can talk, you can bicker, 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 you can talk all you want, but it's different than it was. No, it ain't, no, it ain't. You got to know the territory. That's part of the line. And he would sing that because his point in teaching forest ecology was you've got to know the territory. You've got to understand the glacial history. You've got to understand the parent material, the landforms, in order to understand the forest. So his classes really changed the way I look at the world, literally changed the way I looked at the world, because before that, I really didn't have much understanding of glacial history and how important that is for the upper Midwest. So we're going to talk a little bit about glacial history to start off today. There have been several ice ages that have affected Minnesota. In the last 2 million years, there have been 4 ice ages, and they're named after states that represent more or less the furthest south they reach. The oldest was the Nebraskan state about 2 million years ago. The Kansan glaciation occurred about 400,000 years ago. Illinoisan approximately 150,000 years ago, and then the Wisconsin glaciation occurred approximately 100,000 years ago and ended about 10 or 12,000 years ago. Most of what we see in Minnesota as a result of the glacial history is a result of the Wisconsin glaciation. These are continental scale glaciers that covered large areas. They were hundreds of feet thick, if not thicker, and they carried a lot of debris with them, soil, rock, things like that. And they bulldozed, they buried things that were in front of them, they buried things that they left behind. So they had a very major influence on the landscape as we know it today. This figure shows a composite of the Minnesota glacial history in the Wisconsin stage, and there were several different lobes during the Wisconsin glaciation, several different stages or substages of Wisconsin glaciation. The first was Wadena, and there were other lobes, Rainy, Superior, and the most recent one was the Des Moines lobe. And this map shows the extent of glaciations, or at least it shows the extent of where there's parent material from each glaciation that's exposed in Minnesota. This shows the uppermost deposits from a glaciation event, and so some of the older glaciation events, like the sediments from the Wadena lobe, are often been covered up by Rainy or Des Moines lobe, for example. So the biggest area of the gray is the Des Moines lobe, and that's called the Des Moines lobe because it reached all the way into Iowa to Des Moines. And in fact, there's a hill in the center of Des Moines where the capital of Iowa sits on a hill, and that's part of the Bemis moraine, which is the terminal moraine, and that is the southernmost extent of the Des Moines lobe during the Wisconsin glaciation. So you can also see on this map, there are arrows coming in from different directions, and those represent the directions that these lobes approached Minnesota. And so they came from different locations and they came in different directions. And so they carried different source material. And so you can see on this figure I showed that the different lobes carried till or sediments or soil sediments of different colors, and the different colors reflect a different composition, different origin, and the rocks that they carried represented different types of rock, and the soil sediments, the smaller sediments, represented residuum of those rocks that had been broken down either before the glaciation or during the glaciation period. Okay, now we're going to talk about Minnesota landforms, and there's quite a few different landforms, and I think probably many of you will recognize some of them, if not all of them. But I hope this is informative for you. I think this is kind of fun. I really like driving around the state and looking around the landscape and seeing if I can guess what type of landform I'm looking at and trying to understand the glacial history of it. First thing to understand is that a lot of the landforms that we see today represent what was left behind as the glaciers melted or as they retreated. And so this figure shows a receding glacier, and there's several different types of landforms that it leaves behind as it deposits sediments that it's carrying. And the first couple are moraines, and that's just the sediment. That's a mixture of all the sediments the glacier is carrying and just drops it in place. So the terminal moraine is like what's pushed in front, and ground moraine is what drops out from the ice. And I'll just mention that this slide, I'm going to go through everything really quickly, just introduce these terms, and then we'll go through them one by one a little more systematically in the next set of slides. So the moraines are the material that's just the composite of everything, just dropped in place. There's an outwash plain, and outwash is probably the most intuitive term to understand because it represents sediments that washed out from the glacier. So they were carried by meltwater. And so it's called outwash because it washed out from the glacier. Easy enough. Things like eskers and kames are features that form in the decaying ice, in the melting ice, underneath the ice, or within caverns or tunnels or cavities within the ice. So there's water carried sediments into those cavities, and it settled out, and then they were reshaped when the glacier eventually melted completely. Drumlins are sort of a subset of moraines. It's glacial till. It's dropped underneath the ice. And then there are kettles that are represent where there was a block of ice that eventually melted and left a hole in the landscape that filled in as a lake or a wetland. So this is a breakdown of the different sediment types coming out of a glacier. So collectively, everything that the glacier is carrying is called glacial drift. All the sand, soil, clay, silt, rocks, boulders, all called glacial drift. If it is dropped unstratified, so the ice deposited, it's called it's glacial till, and it's deposited in the form of a moraine or a drumlin. And a moraine is just things that are dropped. And a drumlin is glacial till, but it forms a small hill, and I'll show you some pictures, of drumlins in a minute. Sediments that were carried out of a glacier by water are water deposits, and so they're stratified. And probably everybody in this organization is probably enough of a nerd that sometime in elementary school you did an activity where you put soil in a jar, fill it with water, and you shook it up and you watched it settle. And gravel and sand settled out immediately. Medium-sized particles of silt settled out over time, maybe a few minutes to 10, 20 minutes. And then the clay particles, the finest particles, settled out over a much longer time, over a day or two. And as wetland scientists, we recognize the importance, the relevance of those things now, because we are checking the texture of soils when we're in the field. We're looking at on alluvial plains, on floodplains, where we're looking at silts and sediments and clays, and sandbars, things like that. So we recognize the importance of water in sorting and stratifying their sediments. So again, outwash is just all the sediments that wash out from the glacier, and so there can be stratification depending on the velocity of water that's carrying the sediments. So very fast water will carry everything, including gravel. As it slows down, gravels drop out. As it slows down further, sand drops out. As it slows down further, silts drop out. And then in still water, eventually you'll get clays to settle out. There are two features, cames and eskers, that are called ice contact. And as I described, those are formed underneath the glacier in a cavity while the glacier is melting. And then there can be a glacial lake as the meltwater pours out of a glacier and it's impounded either in a depression or because of an ice dam, it may form a glacial lake. And that will result in a landform that we recognize today as a lake plain. And there may be associated beach ridges associated with that lake. So first of all, I'll talk about moraines. As I mentioned, moraine is glacial till. It's everything that the glacier is carrying. It's unsorted, it's unstratified. It's just dropped in place either as a terminal moraine or an end moraine. And when you look at glaciers and mountains, there are several other categories of subcategories of moraines, but I'm not going to go into those. I just, for our purposes today, I'll just say moraines as all the glacial drift or till that is dropped into place. And so this picture in the lower left is an example of glacial till. It's got every particle size from rocks, cobbles, gravel, sand, all the way down to silts and clays. When a moraine is formed and left behind by a glacier, it'll create either a flat plain that's not entirely perfectly flat, but maybe a little bit undulating, maybe irregular topography, or it may be mounted, or it may create a hill. In the case of a terminal moraine, may actually be a substantial hill. Composition, it's just a mixture of everything. And the properties of that soil, of that parent material, and as the soil that develops from the parent material, it may be dense, it may be moderate to have low permeability, depends on the clay and the sand content, and that can vary from location to location. It can vary from the sublobe or the lobe of the Wisconsin glacier that deposited the sediments. Drumlin, as I mentioned, is sort of a subset of glacial till, and these are small hills that are formed underneath glaciers, and they're comprised of till, and they form these little hills, and they're elongated hills, and the narrow end points in the direction that the ice was flowing. And because they're made of till, they're often a mixture of all kinds of different soil sediment types, and they often form fields of clusters, and they'll call them a drumlin field. So these are examples of some drumlins, and this picture on the upper right is a picture of a road. When you build a road across some drumlin fields, you get these undulating, these ups and downs as you go from the top of the drumlin to the bottom and back up and down. Looking at a three-dimensional representation of what a soil profile or soil associations might look like in a morainal landscape is shown in this figure. And I got this figure, and there's some more I'm going to show you from some old soil surveys. Like I love the Web Soil Survey because it's the most up-to-date mapping information, and it's updated with the most recent information as maps are refined. And there's a lot you can do with it. You can color code for hydric soils or permeability, drainage class, things like that. But I like to go back to old soil surveys, and you can find PDFs of the old soil surveys that are anywhere from 20 to 50 to 60 years old. And in those, they will often give you a description of different soil associations that are common in that county. And often they'll present a three-dimensional figure like this of the soil association. And I like this because it gives you a different way of looking at the soil association than your soil survey map. You get a map from the Web Soil Survey. It's a two-dimensional map, and you can color code the different polygons, which is great. But then this three-dimensional representation helps you understand the different soil series as they relate to each other in three-dimensional space on the landscape, which is really important for understanding wetlands, because whatever we're doing in with wetlands management, restoration, mitigation, delineation, we're trying to work with a three-dimensional object or three-dimensional area on the landscape. And so I love these figures because they show the three-dimensional nature of the soil associations. So one thing that's noticeable about this figure is there can be a random location of wetlands. Moraines often leave an irregular, undulating topography, and there doesn't seem to be any rhyme or reason of where wetlands occur. They're undulating, there's highs and there's lows, and so wetlands can be found all over in these low areas. And often I found them to be they're of a smaller scale than are detected in a soil survey or a national wetland inventory. So if I see a morainal soil in an area that, for instance, where I'm going to do a delineation, I know I need to be alert for this undulating topography and wetlands that might not be present either on aerial photographs or on the soil survey or on the national wetland inventory. And then there are larger areas where there's a kettle, and I'll talk about kettles in a minute. And the kettle is where you may find a larger wetland, maybe a large peatland, maybe a coniferous swamp, something like that. And those will be found often on morainal landscapes. Eskers and kames, as I described earlier, are considered to be ice contact features because they form underneath melting ice. So that this example on the upper left shows melting ice, and there's water cracks that are forming in the ice, and there's meltwater that's flowing into it. And as more meltwater flows into a block of ice, more melts, and so it creates these cavities or these chambers in the glacier, and it may run out and run out of the glacier and be deposited someplace. But these are essentially little rivers or caves within the glacier, and they're carrying sediments, they're carrying rocks and gravels and things like that with them as they go into these glaciers, into these holes. And the finer sediments are easily carried away because they don't settle out for a while, but a lot of sand and gravel are deposited in these cavities. Well, you can see on the left, like this is constrained, this tunnel is constrained, a tunnel of ice is constraining the sand and the gravel. But when that ice melts, then the constraints are lost. And so it's stratified as it's laid down within the glacier, but as that ice melts, then it loses its form. And so I describe it as partially stratified, because it was stratified when it was laid down within the ice. When the ice melted, then it slumped. And so you can find sand and gravel, you can find some striations, but along the edges especially, the stratification is lost because of the slumping. And if a landform is formed that's just a mound or a hill, that's called a kame. And if it's a long, sinuous ridge that was formed in essentially a river underneath the glacier that formed in the river, then the resulting landform that we see today is an esker. And so these are either exist as hills or ridges. And so I got a couple examples of an esker on the top right and a kame on the bottom right, and those are ice contact features. They're important in many cases for sources for aggregate because of the sand and the gravel. A lot of eskers and kames are desirable targets for aggregate mining operations. Now, kettles are formed by a block of ice of a melting glacier that's left behind, and it gets covered either with drift from a moraine, or it gets covered with outwash. That's materials that wash out from the glacier. So that chunk of ice is embedded within the sediments or it's completely buried. Well, eventually after the glacier melted and the ice age ended, that block of ice melted and it left a hole in the landscape. And those holes in the landscape formed lakes, and they formed prairie pothole wetlands, and they're called kettle lakes, potholes. And so southern Minnesota into the Dakotas, there's lots and lots of prairie pothole wetlands and lakes that are formed as kettle lakes, and throughout Wisconsin, Minnesota, all are, we so many lakes, and a lot of them are formed by this kettle process. And so the bowl was left, and in some cases they remain as a lake. In some cases they became wetlands, and they are formed in glacial outwash or till. Here's an example of area in southern Minnesota, the Soil Association prairie pothole wetlands, that the base landscape, the apparent material underneath is glacial till, where there were ice blocks left and formed these potholes. Now you have wetlands or lakes. And so there's, you've got silt loams, clay loams on the upper portions of the landscape, and in the bottoms, in the low areas, you have silty clay loams and muck in the bottoms of the potholes. These potholes often lack an outlet. That's 10,000 years is fairly young for a landscape. And so a lot of these don't have outlets. Eventually, given a million years or more, they would find more outlets as they eroded, and so some of these would be drained. But being such a young landscape, we still have a lot of potholes left. And this landscape, especially in southern Minnesota, is often capped by loess, which is windborne deposits. And we'll talk a little bit more about loess in a few slides. But it's a windborne deposit that settles silty sized particles over the top of glacial sediments. Here's an example of a kettle lake, and this diagram was published in 1941 by Lindemann, and this is from the Cedar Lake or Cedar Creek nature area north of the Twin Cities. This is Cedar Bog, and this was started as a kettle lake, and over 10,000 years of succession, there's been deposits of marl, there's deposits of coppergenous earth in the bottom of the lake, and there's deposits of peat, sedge, and forest peat as this lake had succession through wetlands and to a conifer swamp now surrounding it. So the open water area is now just a fraction of what it was at the end of the ice age, and it's surrounded by a coniferous swamp. So understanding the evolution, the origin, succession of this type of a wetland all starts with understanding that it was formed as a kettle lake at the end of the ice age. Outwash plain is a large area of outwash that is material that's washed out from the glacier, and it's typically relatively flat and moderate slope. They're not always completely flat, but you see some pictures here where it's very flat. And these are pictures from the Anoka Sand Plain on the northwest side of the Twin Cities. So there are areas there where it's very flat. It's not always flat. There can be some inclusions of moraine and some other reasons. There might be a little bit of topography. But the parent material coming off the glacier is a lot of stratified sand and gravel. Again, fine sediments, clays, and silts were carried away by moving water. And this is sands and gravels that washed out from the glacier. A lot of drainage ditches now present on the Anoka Sand Plain that were created 100 years ago to make these areas more approachable or useful for agriculture. And then you get a soil profile like this. And I'm originally an Iowa farm kid from south of the Bemis Moraine, so from south of the end of the Wisconsin glaciation. So this type of soil profile still looks foreign to me. This is soil profile that was in a drained wetland on the Anoka Sand Plain. There is organic peat that's drained on the top, and then once you get through about 2 feet of the peat, it's just sand, and it's just almost pure sand all the way down. And it's just amazing to me to look at the soil profile and just see there's just tens and tens of feet on top of sand on top of sand that was glacial outwash. And in this particular site, I did some soil descriptions down to 15 feet. And there are a couple places within the soil profile where I would find coppergenous earth, which is lake sediment. So this had a complex history. It wasn't all outwash from one glacier melting event. There was sand, there was lake sediment sand, and then peat. So there were different times. There was outwash, there was a glacial lake, there was more outwash that filled in that lake, another lake, more outwash, and eventually a wetland that formed on top of that. And then with European settlement it was drained, it was ditched and drained, and now it's, a lot of these are becoming housing developments. So this is a soil association from the Anoka Sand Plain. I know a lot of people in this group are wetland delineators, and as such, one of the highest growing areas, fastest growing areas in the Twin Cities area is in the Northwest Metro on the Anoka Sand Plain, Blaine, Anoka, Andover, Elk River, those types of areas. And so in those areas, if you've done delineations in those areas or mitigation banks, things like that in those areas, you'll recognize this Lino, Zimmerman, Isanti soil association. There's rifle, and there can be marky mucks in the lowest areas. There's Zimmerman and Sartell soils at the higher areas, and those higher areas are very sandy. They're excessively well drained, and so you get things like black oak that grow there, or northern pin oak on those drier sandy knobs. And in the lower areas, you can get large areas of peatland, and some of those peatlands have been drained for farming or for sod farming. So some of the larger sod farms north of the Twin Cities, you can just drive by on the highway, you can recognize that as a sod farm and know that is that's a drained wetland. It's on peat, on drained peat, and it used to be a wetland on the sand plain. Lake plains are formed by glacial lakes that formed while the glaciers were melting. And there was obviously, if you have continental scale glaciers that are hundreds of feet thick with ice, that's a lot of water. So as it melts, that water has to go someplace. And so, the rivers, the lakes, the rivers we recognize were formed from the melting of those glaciers, but then there were larger lakes that existed at different times during the melting of the glaciers at the end of the Ice Age. The largest is Lake Agassiz, and this top figure in the top left shows the maximum extent of glacial Lake Agassiz, and some people speculate that it may have been the largest body of fresh water that ever existed anywhere in the world. I know that's kind of hard to verify or disprove. And it is my understanding that it was probably not ever this large at any one time, that the lake level varied at different times. It was the lake size and level reflected the location of glaciers, how much water had melted, and it was often dammed up by glacial ice. And there are several melting pathways channels where it drained to the ocean through different pathways at different times. So it was a very dynamic thing, probably over thousands of years, that existed at different levels and in covering different areas. But the whole large area was extremely large, as you can see from this. And one of the notable drainage ways is important for Minnesota, because at the southern end of that, near Ortonville, near Big Stone County, in that area on the west central border of Minnesota, is where a glacial ice dam broke with a catastrophic draining of glacial Lake Agassiz, and that created glacial Lake Warren. And glacial Lake Warren carved the Minnesota River Valley as we know it. So the Minnesota River that exists today is too small of a river to have created that large of a river valley. So it was glacial Lake Warren that carved that, and evidence suggests that it would happen in a fairly short amount of time, not over hundreds of years, but over a relatively short amount of time after a catastrophic break of an ice dam, and it created the big river valley that we know today, that came all the way to the Twin Cities and where it met with the confluence of the Mississippi River. The map on the bottom left shows the extent of large glacial lakes that have been documented in the state of Minnesota. So glacial Lake Agassiz covered a lot of the northwest part of the state, but there are other glacial lakes that existed at different times, and you can find parent materials, you can find glacial lake plains associated with some of those. In some cases, they may have been covered up by subsequent, a later glaciation event, like the Des Moines Lobe was just the last glaciation event. The sediments, the soils that you find in those, the parent materials were formed from sediments, fine sediments that settled out in still water of a lake. So there's a lot of clays and silts, they're stratified, there's low permeability because of so many fine materials. You can also find areas where there might be sands and gravels where there was a delta that poured into a lake, but overall, in general, lake plain's pretty flat with pretty fine sediment particles. And so that affects, what we see for wetlands today. Here's an example from glacial Lake Agassiz lake plain in northwest Minnesota. Some of the soils you see, Colvin, Fargo, Hagney, Perella, they're all pretty flat. There's not much differentiation in topography. They're all silty clay loams, poor drainage, low permeability. So would be a pretty wet landscape if it's not drained. It's very productive farmland. It's great for farming if it's drained. And so now you see in the glacial Lake Agassiz Lake Plain, see all these fields, and they're really big fields, and there aren't hills and moraines and river valleys. So the farm fields are very big. Glacial beach ridges also can form an association with glacial lakes. And glacial Lake Agassiz existed for a long time at different levels. And the wind and the wave action along the shorelines created beach ridges. And the turbulent water would remove fine sediments, the clays and silts, and leave sands and gravels. And so there are descending, stair-stepping sort of low ridges that are still in existence that are glacial lake ridges. A lot of sand and gravel, high permeability, very porous. And again, these are attractive targets for aggregate mining operations. And I'm going to talk about calcareous fens again in a little bit in a few minutes later in my talk. And a lot of calcareous fens are found at the base of glacial beach ridges. So there's sometimes a conflict between dewatering for an aggregate mining operation and the groundwater that supports a calcareous fen. And this happens quite a bit. There are quite a bit of occurrences of calcareous fens in northwest Minnesota along the glacial beach ridges. Here's on the right is a picture of the web soil survey of an area of glacial beach ridges. And you can see on the right side there, you can kind of see the orientation of the beach ridges from the aerial photograph, the signatures that the beach ridges make. And there are the topographies. There's not a lot of topographic difference. They're usually not hugely distinct ridges, but kind of lows, up and downs. But they show up on the aerial photograph, and they create a really complex soil survey map because there's so much interspersion of different soil types depending on whether it's a low or a high, and depending on the composition of the sand and gravel and silts and things like that that are in the beach ridges. This is a couple of figures from the same area in northwest Minnesota, and two different figures of the basically the same area, and it's part of the same area that I showed previously in the previous slide of the soil survey. So on the left, then it's practically the same photo on each side. It's just two different things shown. On the left, I show a true color aerial photograph, and on the right, it's a shaded relief map, and I've got 50-foot contour maps. So the lake plain on the far left of each photograph is really flat, nearly flat. And then you've got a series of contour lines going up, 50-foot contour lines. And so in the space of about a mile or two, you go up several hundred feet in elevation off the lake plain as you climb these glacial beach ridges. And then when you get to the upper summit, it's a till plain. So it's a glacial moraine, it's a ground moraine. And so it's hummocky. There's highs and lows, there's kettle lakes and kettle wetlands. And you can see that in the aerial photo, and you can see the irregular shape of these topographic lines. It's because of these irregular topography created by the moraine. And then you contrast that with the glacial beach ridges, these regular contour lines created at the lake shore. And then you get again back to the lake plain, and there's no contour lines. It's just flat because that was open water when it was glacial Lake Agassiz. Here is a soil association from a beach ridge area. And there, like I said, there's a lot of sand and gravel, so they can be excessively well drained on beach ridges. They can have wetlands in low positions, and in large areas, like in the very northwest part of the state, in low areas on the glacial lake plain, you can have peatlands that form. This particular diagram shows that the parent material is sandy glacial lacustrine deposits. And way I would describe that, or way I understand it, is glacial meltwater that was deposited into a lake. So it could represent an outwash delta in a glacial lake. So you get a lot of, so it's both, it's a combination of lake sediments and outwash sediments. So they call it glacial lacustrine sediments. And in a lot of cases, it probably represents an outwash delta in the lake. Here's another diagram that shows beach ridges. And this diagram of soil associations kind of reflects the picture of the soil survey I showed you before with these long, narrow soil series because they reflect the different ridges at different times at different topographies. And so you've got these repeating ridges, and they're long and narrow. Again, excessively drained on beach ridges. You can have interspersion of highs and lows, and you can have wetlands in low positions. But the because of the high drainage, the high permeability of the sediments, because of the sand and gravel, you may not have a lot of wetlands there because it's so much drainage. I'll share a fun fact with you related to these beach ridges. Minnesota, I learned this last year, Minnesota is the nation's leading producer of kidney beans. And it's because kidney beans love to grow on these glacial beach ridges. They have a shallow root system. They like the porous, sandy, gravelly soil. They're often irrigated on these beach ridges because the water table doesn't stay very high. But up in northwest Minnesota on these glacial beach ridges, you can find lots and lots of fields of kidney beans and sometimes black beans. And it makes Minnesota the leading producer of kidney beans. So another thing that relates to geomorphology. Why is geomorphology important? Well, it gives us kidney beans. If you look up where Minnesota grows potatoes, there are 3 regions where there's a lot of potatoes grown, and those all reflect different geomorphic regions reflecting different glacial histories as well. So it's kind of cool that it's not just wetlands and native plant communities, but it's also agriculture and industry that are founded on or based on or have some connection to our glacial history and our state's geomorphology. There are a couple areas of older till in the state, and those are in the southeast and southwest corner. And there is till that's either of Kansan or Illinoisan age, and it's covered with loess. So Kansan or Illinoisan, if you remember from one of the early slides, those are sediments, that's glacial till that's hundreds of thousands of years old. And that was deposited so before the Wisconsin glaciation, and those areas were not covered by glaciers during the Wisconsin glaciation event, but they have been covered up with loess. And loess is wind-blown sediments, predominantly silt-sized particles, and in some cases that can be several feet thick of loess that have been deposited on top of this older till. And the loess, is my understanding, the origin of the loess is from the Great Plains, especially during the into the Ice Age, when you had these outwash plains and you had these westerly winds coming across outwash plains. They were picking up a lot of the finer particles, the clays and silts and things like that, and carrying them further west. And some of the silt particles got dropped in Minnesota and elsewhere in the Midwest, further south in Iowa. So like I said, I was an Iowa farm kid. So growing up, I was used to understanding that our soils in that area in southern Iowa were all loess over ancient glacial till. And in some places in western Iowa, there are large formations of loess. So they call them the loess hills along the Missouri River Valley, on the east side of the Missouri River Valley. The westerly blowing winds deposited large amounts of loess that form these hills that are kind of a unique feature in Iowa now. And in these areas of older loess or older till with a loess mantle, you have a more drained, more dissected landscape than the younger glaciated landscape. And you have this dissected till plain capped with loess, and you don't have the occurrence and the frequency of the kettle hole or the kettle lakes or the prairie pothole wetlands, because this landscape has been draining and it's had erosion for many hundreds of thousands of years, more than most of the state of Minnesota that's only been draining and eroding for 10,000 years. So there, a lot of wetlands, you find along drainage features. You don't find as many random locations of pothole wetlands. And then we're going to talk about the driftless region. It's a unique area in the southeast part of the state, and includes a good portion of Minnesota, and most of the driftless region is in Wisconsin. A portion of it's in Iowa, and little portions in Illinois as well. And this is an area that's called driftless because it has little or no glacial drift. So it was missed by the continental glaciation events going all the way back to the Nebraskan event. And this diagram on the upper right shows the different glaciation events, Nebraska and Illinois and Kansas and Wisconsin events, where they all seem, for whatever reason, missed this part of the country. They missed this area in Minnesota, Wisconsin, Iowa, and Illinois. And so this landscape It's just a beautiful area. It's much more dissected because it's had millions of years of erosion rather than tens of thousands or hundreds of thousands. It's had millions of years of erosion to create the landscape that we know today. So you got these great valleys that are just picturesque valleys, and these bluffs and these hills and these plateaus up above. And in an aerial photograph, you can see this really dendritic pattern of the valley erosion. And so this aerial photograph shows La Crosse, Wisconsin in the center on the Mississippi floodplain, and then on either side is Wisconsin on the right and Minnesota on the left. And you can see this really intricate dendritic branching pattern of the valleys that you don't see that type of really intricate erosional pattern elsewhere in the state of Minnesota. So the parent materials in the driftless region are not glacial drift. They are not outwash, not ice contact features. The parent materials are mostly derived from erosion of rocks over the millions of years. So residuum from rocks capped with loess. At the bottom base of hills and bluffs, you get colluvium, and in the stream valleys, you get alluvium. And alluvium is a much more recent thing. It's something that's reworked or deposited and eroded every year. This figure, incidentally, comes from the Department of Agriculture. They got some great figures that are available on how groundwater moves in southeast Minnesota. So this is taken from an area with karst topography, and it shows how the groundwater moves from the upper plateaus and comes out in springs, and there can be disappearing streams. And there, you can see there's a stream, there's wetlands in this alluvial valley. And that's where that's gonna tell us a lot about where you find wetlands. Again, no prairie pothole wetlands in this area because it's so dissected and so eroded over 2 million years of erosion, at least 2 million. You find wetlands along streams, you find them in floodplains, and you find them in seepage zones. There's a lot of springs, a lot of seepage in these areas because the bedrock is limestone and dolomite, so it has a karst topography. Those types of bedrock dissolve with water moving through them. So for all the millions of years they've had water moving through them, there's a lot of groundwater movement, there's a lot of springs, a lot of seepage wetlands. And then one more comment on landforms, and this is alluvial landforms, and these are younger landforms than the glacial landforms that we've been talking about because they're very active. They're in floodplains with dynamic rivers. So every year you've got erosion, you've got deposition, you've got the new channels being created, channels being cut off and creating oxbow lakes and creating wetlands. So it's a very dynamic, much younger landform, but it's also one that we should recognize as and very important for wetlands. And if you're a delineator, sometimes they are difficult to delineate on because they're so active, they're so young that often you have a wetland where there's alluvium and there may not be time to form redoxomorphic features for determination of hydric soil. So they're interesting, but they can be frustrating. And when putting this slide together, I learned a new term, Yazoo stream. I've seen streams like this on floodplains, but I never knew there was a word for that. So this figure I found to put on here has the term Yazoo stream. And so that's a small stream that runs parallel to the main stream, and it's often separated by the levee. The levee is formed by annual cycles of high water and flooding and sediment deposition. And then periodically the Yazoo stream will find an outlet where it will reach the stream, the mainstream. So I thought that was kind of cool. I learned a new term putting this talk together. So a summary of our landforms and parent material. We have glacial landforms, unstratified types of till, moraines and drumlins. Stratified till includes outwash, which is, as I said, it's easy to remember because it's material that washes out from the glacier. Ice contacts features eskers and cames that form underneath glaciers and then are left behind and slump when the glacier melts. And then you have glacial lakes that form a lake plain and beach ridges, glaciers left behind, blocks of ice that melted and form kettles. And then there are non-glacial landforms that are important. In some parts of the state, loess, especially in the southern part of the state, residuum, colluvium in some areas, and then alluvium in stream valleys and floodplains all over the state. And I recognize there are a couple of things I'm not mentioning, talus slopes, which is really kind of related to colluvium, and the shallow bedrock or exposed bedrock lakes and things like that are the border areas. I'm not really talking about that today, but those are important in their context. But as far as like a large areas of the state, these are the important landforms for understanding wetlands and wetland ecology. So what can you do with this information about geomorphology? So I would offer that you can better understand the landscape, better understand water flow and the occurrence of wetlands, the types of wetlands and the locations of wetlands are not entirely random. There's a certain amount of randomness to it in terms of like where outwash formed or where a kettle lake formed. But these processes are not random within the state. And so when you're in the prairie pothole region, you see this type of a pothole wetland formed over and over and over because the same geomorphic process formed the parent material, which formed these pothole lakes, for example. You can combine this information with other geomorphic approaches in your work for whatever purpose you need. And I'll show an example with wetland delineations in a minute. And then this type of geomorphic information helps understand the occurrence of native plant communities. It helps understand landscape ecosystems and the ecological classification system that's been developed by the DNR. So one thing that can be complicated is that I talked about the multiple glaciation events, so multiple ice ages, and then multiple lobes or multiple stages of the Wisconsin glaciation. So I'm showing this figure again that shows these different lobes of Wisconsin glaciation period. And this figure shows what was left at the surface. And so you've got Des Moines lobe, Rainy lobe, Superior lobe, Wadena lobe, and I showed those in a table before, but this figure also talks about Brainerd slub lobe and the Itasca lobe. And it's my understanding those are recognized as sublobes or later stages of the Wadena lobe. And then there are other tills, the older tills, and then there's the driftless area. So you can get a complex site where you have multiple layers of things. And I talked about this, I alluded to this with my discussion of a sand plain, on the Anoka sand plain, where there was a peat formation on top of outwash, on top of lake sediments, on top of outwash sands. And in the center of this slide, I show an example. This is from the book Minnesota's Geology. And this is a cut section from exposures near Hot Creek in Renville County. And you can see at the bottom, there's Wadena lobe. So that was the oldest glaciation during the Wisconsin glaciation. On top of that is sediment from the Superior lobe. On top of that is lacustrine sediment. So there's a glacial lake that formed. And then on top of that is Wadena lobe again. So there was a re-advance of the Wadena lobe. After it advanced once, it retreated. The Superior lobe came in, a nice glacial lake formed. And then the Wadena lobe advanced again. And then it retreated. And then the Des Moines lobe advanced and left the last deposits on top. So that's kind of a complicated stratigraphy. And so you can imagine, this shows like what it might look like at a road cut, but you can imagine this could be stretched out over a mile or many miles over the length of a county or several counties where you have, different deposits from different lobes, different glaciation events, and the sediments that were left might be discontinuous. They might have eroded. Some of them have been lost through erosion or whatever. So the point is it can make things look a little more complicated. So I gave you the simplified version of here's a moraine, here's an outwash plain, here's an esker, and so forth. Well, once you get into the real world, it's a little more complicated. And so here's an example then on the right side of a soil that I encountered in the last year, the Cutaway Soil Series, and it's formed in moderately well-drained soils from a sandy glacial outwash. Okay, that's great, that makes sense. That's outwash or aeolian mantle. Okay, aeolian mantle, that's loess, that's wind-derived, and underlying calcareous loaming tills. Okay, so there's outwash or loess on top of till, on top of moraine, and these soils are on moraines, lake wash till plains, or glacial beach ridges. It's a little bit of everything going on. There's a lot going on in that soil series. So it's not an easy thing to go out and dig a soil boring at this point and probably, oh, well, this was outwash or whatever. It's like, there's a lot encompassed in this particular soil series of Cutaway. There's some, the important thing is that there's some outwash, there's some stratification, but there's also till involved. And so, glacial beach ridges, till plains, moraines. So there's a lot going on in that soil series.
There's a question.
Yeah.
What formed the stone line?
That's a good question. That would have been, I don't know the exact answer to that. That would have been something that would have been just left behind from the glacier. I actually ran across that when I found that figure in the geology book that it mentioned that, but I don't have a good explanation of a mechanism, so I'm not going to speculate too much about that. But it's interesting that that stone line is formed right at the junction of the two lobes. But I can't explain the mechanism to you. But I'm curious now. I'm going to have to dig into that and try to understand that. Any other questions right now?
That was it.
Okay, thank you. As wetland scientists, wetland professionals, we are often looking at soils, and I've been talking about glacial landforms and glacial history and other landforms that aren't glacial related. So that's the parent material. There are 5 factors in soil development. I got this nice information from the Extension Service website, parent material, and there's this slide that shows predominant parent material in different areas of the state, but there's also climate, biota, topography, and time. And what happens over time. You have weathering, you have erosion, you have flooding, you have deposition, you have subsidence, you have organic accumulation, you have drainage, you have grading, anthropogenic grading and earthwork and draining, things like that, tiling. So there's a lot that happens after the parent material is left behind that affects what we see in the soil when we visit a site and we're trying to understand the wetlands, for example. Parent material in this glacial history or no glacier history is important as a starting point to understand that. There are other approaches to geomorphology. A couple of them I'll show here is the hydrogeomorphic classification that was got a lot of discussion 10 or 20 years ago about ways to a different way to classify and describe wetlands. So it's a sort of a different refinement away from the coordinate system and classification. It's kind of a refinement of that than the major systems in hydrogeomorphic classification of riverine, depressional slope, mineral, soil flats, organic soil flats, estuarine fringe, lacustrine fringe. So those things aren't mutually exclusive of the landforms I was talking about, the geomorphic formations related to glacial history. But you can see how they would plug into there. So depressional, it could be, on an alluvial plain, it could be on an outwash that's got some sloping to it, or it can be a depression on a moraine. And then you can also consider landscape position. And this figure shows landscape position in relation to relative position on a slope, on the summit or on the mid slope, back slope, toe slope, that kind of thing. So where do you use those things? Well, one of the ways places you use that is on a wetland determination data form. There is that line at the top for landform. Well, what's it asking for? Is it asking for the glacial landform after my forest ecology class at University of Michigan? That's what I want to put. That's the first thing I look for when I visit a site. Is it a moraine? Is it glacial? Is it outwash? Is it lake plain? That sort of thing. So that I want to put that, but then that doesn't always tell the whole story. So then I pick and choose from the HGM categories, and I pick and choose from the landscape position and from the glacial position. So maybe I would say I'm on the toe slope of a morainal landform. And then I describe the local relief, concave, convex, and so forth. So I pick and choose whatever is most informative at that time for whatever that purpose. If it's wetland delineation, or if I'm writing an EA and I'm trying to describe a site, I'll look back to like the parent materials and the glacial landforms, and then what's happened since then. So I think there is no right answer on what system you use. They're different, and I think they can be combined and used as needed to suit whatever need you might have. Now let's talk about the ecological classification system. These are a couple figures I've shown before. The one on the left, I want you to recognize again where the glacial lakes are. This also shows moraines, and it shows 3 drumlin fields. It shows the Toynbee drumlins, Piers drumlins, and Wadena drumlins. So those aren't the only places you can find drumlins, but those are significant areas where you can find a distinct drumlin field. And the moraines are in moraines. But what I really want you to get out of this figure is the position of glacial lakes, and then look at how that compares to this map on the right of soil parent materials. So a lot of these glacial lakes are associated with lacustrine parent materials. So they're glacial lake plains that we still recognize today. Some of those glacial lake plains are maybe overlaid with outwash or till now, so they're not the glacial lakes aren't the parent material. So it's not the uppermost sediment from the glacier. It's not the ultimate parent material, but the parent materials include glacial lakes. till and bedrock, lacustrine sediments, the glacial lakes, outwash, and just till from in moraines and ground moraines. So think about those two figures when I go to the next slide. And the next slide is the ecological classification system. And on the left, it shows the provinces that we're all very familiar with: the Laurentian mixed forest, the tallgrass aspen parklands, eastern broadleaf forest, and the prairie parkland. And those reflect partly the glacial history and partly climate, but they're very much related to the glacial and geomorphology and glacial history, or in the driftless area, the lack of glacial history. And then if you move to the right, that's the next hierarchy, next level down in the hierarchy in the ecological classification system. These are subsections, and these subsections identify very strongly with the geomorphological history, be it loess and driftless region or the glacial history in the rest of the state. Very strongly, these regions are very strongly correlated and defined by the glacial history. And you're probably all familiar, most of you probably are familiar and use these books, the field guides to the native plant communities of Minnesota. I just love these resources the DNR has prepared. It took many people working many years to put these together. It's a great resource to help make sense of the native plant communities and the diversity and the landscape and the ecosystems in Minnesota. So there's three guides for the different provinces, and two of the provinces are combined in the prairie parkland and tallgrass provinces. Well, if you look at these, they describe native plant communities, and there's some introductory material explaining how to use the book and some introductory material on statistical analyses of Railevay data that were used to develop these classifications. And I'm going to talk about that, and then I'm going to take some examples of some native plant communities and show how that relates to the geomorphology and the glacial history that determines what types of ecosystems and native plant communities are found today on those landforms. So in the beginning pages of these field guides, they show these ordinations, and this is a type of multivariate analysis. It's kind of similar to principal component analysis, where you have lots of variables, multivariate analysis, and it's a particular type of multivariate analysis called ordination. And so what they do in this analysis, they look for the variables that explain the most of the variability in data. And in this case, the data would be physical data on soils, topography aspect, nutrients, soil textures, things like that, as well as biological things like understory, shrubs, forest overstory, biological data, all goes into that, these multivariate analyses. And the analysis looks for the major variables that correlate with each other that explain the variability in the data. And they've come up with these two major axes. And on the left graph, you can see this is for wooded, upland, and wetland classes. And each one of these points on here represents a native plant community type. And I'll talk about what the codes mean in a minute. So each one of these points is a different type of native plant community. And the axes on here correlate to nutrients. And there's a whole bunch of variables that would go into that. So it's going to be things like soil texture and landform. There could be variables involved in that axis that represent nutrients, and there's poor nutrient availability to high nutrient availability on the right side of the x-axis. And on the y-axis, it reflects a moisture gradient from dry to wet. And then they put a dotted line to show a separation between wetland and upland systems. So they put in all these different wooded types, and then they can draw clouds around them. And so like you see this pink cloud in the middle, these are all FD. This is a fire dependent forest or woodland system. And in this green cloud, this is MH. So that is a mesic hardwood. So it's kind of cool that you take all these variables, you plug them into this analysis, and it clusters that there is correlation to variables of these different ecosystem types. And then the right graph is of upland wetland classes. And so a similar organization just on wetland types. And so I think it's really cool that you can put all this data in, you can get this multivariate analysis that actually makes sense of something. And then when you group these, you can see there's the relationship. These axes explain something. When you look at the variables that are involved, you can see that this axis, the x-axis, reflects nutrients or mineral composition, and the y-axis reflects moisture. We take two of these plant communities as an example, and I've blow them up a little bit with yellow dots. So I chose the FD-N12, and that is the northern dry sand pine woodland. And we're comparing it to the MHN46, the northern wet mesic hardwood forest. So in that code, there's an ecological system, a geographic region, and then moisture nutrient category. So the ecological system, FD, means fire dependent, and MH means mesic hardwood. So you've got kind of a dry forest that burns occasionally, and you've got a more of a mesic forest that doesn't burn as much. The disturbances are more likely to be wind throw and old age and insect and pathogens, and loss of trees is going to be from natural dying or from wind throw. Geography, then they organize these into different geographic regions: central, northern, southern, and for the wetland and grassland communities, there's also a prairie category for geography. Now, the next two categories, these numerical codes, reflect geomorphology. So the first digit reflects that y-axis is a moisture gradient. So a value of 1 is a drier site and a value of 4 is a wetter site. And the second digit represents nutrients, soil nutrients. So 2 is fewer nutrients, 4 is more nutrients. This code, these digits on these code reflects geomorphology. So you can flip through these books, you can see these different numbers, and they tell you something about the geomorphic history. They tell you about the landform, the properties of those landforms that determine the occurrence of these native plant communities. So I think that's really cool because this code ties directly back to all these geomorphic landforms that I was talking about earlier. And then if we go further and dig into the description of these plant communities, it more explicitly tells you about the landforms. So this fire dependent community, I put boxes on here on the different landforms that it's found on. Outwash plains, parent material is well sorted sand, occasionally with lenses of gravel. Okay, that's consistent with a dry site. I said this is dry, and the ordination shows this is on the dry end of the moisture gradient. So sand, gravel, that makes sense. They're very permeable soils, so they drain very well. So it's a drier site. So it's going to be less moisture in the biota, so there's more likely for forest fires to occur in this forest. Lake plains, okay, lake plains, that doesn't make sense because I told you earlier, lake plains is really silty and clay, except read further, lake plains level, parent material is well sorted, fine, sandy lacustrine sediments lacking gravel or stone. So it's sandy. So again, it's droughty. So where you find it on a lake plain, it's not in the silty clays on the lake plain. It's where you have a localized area of sand that's well drained. And then stagnation moraines. Okay, that's kind of surprising. I wouldn't have expected it in moraines, except read further. It's present on flat, local deposits of sand and gravel within an otherwise hummocky landscape. Okay, so this gets back to the slide where I made the point that these are complicated because it's not, you don't have things just well apportioned in the landscape. You've got overlap and multiple things. So you have a moraine, but you have, sand and gravel area, probably from outwash in a local area on this moraine. And that's where you get this dry woodland that forms on a moraine. So compare that with the mesic forest that shows up on till plains. Okay, either calcareous or non-calcareous till, that makes sense. So a mesic site, so there's a lot of nutrients, there's good moisture availability. A till plain has a lot of finer particles, clays and silts in it, so there's a lot of capacity for that soil to hold moisture and a lot of cation exchange capacity, so the soil has the ability to hold nutrients. So the parent material has nutrients and has the ability to hold nutrients long term, so the nutrients remain available. So that's why you get a more mesic site and you get this northern hardwood forest that does not burn as often because there's more moisture. And you get different tree compositions, so you're going to have more maples and basswoods. Opposed to the woodland, you're going to have aspens and pines and things like that. Other landforms, stagnation, moraines, and glacial lake plains. Okay, that makes sense because again, we've got a lot of silts and clays in those soils. So that's why this is how the geomorphology and the glacial history determines where the northern dry sand pine woodland is found, and determines where the northern wet mesic hardwood forest forms. It's not a random thing. There's a really strong correlation with the glacial history and the occurrence of these forest types on the landscape. Now, looking at wetland types, I've got two to compare here: northern poor fen and prairie extremely rich fen. Northern poor fen, APB N91, call it a northern poor fen, dominated by hummocks and hollows, fine leaf sedge, low ericaceous shrubs. So something that you might call, if you don't go through this process of keying things out, with this guide, you might call this, it's a bog. It's very similar to bogs. It looks similar to bog, has a lot of overlap with some of the species, but it's going to have some plants that are found on where there's a little more mineral nutrient availability than on a pure bog. And then OPP93, prairie extremely rich fen. Another name for that native plant community, that ecosystem, is a calcareous fen. So this is the type of calcareous fen that's protected under the Wetland Conservation Act, the one that is perhaps the most rare wetland type in the state and in the upper Midwest. So let's look at the, let's look at where they show up on this ordination diagram. So they're a pretty similar spot on the y-axis in terms of moisture. They're in different spots on the x-axis, so they're different locations on the nutrient gradient. So the northern poor fen is more the nutrient poor area, and then the rich end is where you can find the calcareous fen. And this one says mineral nutrients. So calcareous fen actually may be low in nutrients in terms of plant nutrients, but it's high in minerals. So whatever the status of soil plant macronutrients like N, P, and K are, it's very rich in minerals like calcium carbonate, magnesium carbonate in the water and in the soil. So let's look at the parent material where these plant communities occur. On peat-filled basins, on nutrient-poor outwash plains or scoured bedrock terrains, or on non-calcareous till. So parent material does not have a lot of nutrients, or it does not have a lot of capacity to hold and make nutrients available. Very sandy, no nutrients not available, low cation carrying capacity, cation exchange capacity for the ability to hold nutrients. Compare that with the calcareous fen, the prairie extremely rich fen. It's found where there's an uninterrupted diffuse discharge of mineral-rich groundwater. And then jumping down a little bit, it's limited to regions of calcareous drift or bedrock. Calcareous, where there's a lot of calcium carbonate, where it's mineral-rich. So again, the occurrence of these two plant communities, they're both dependent on groundwater discharge, but they're very much related to mineral discharge in the waters, which ties directly back to the geomorphology and the glacial history of this site, or the sites where each of these would occur. So again, plant communities very much linked to geomorphology. So I'm going to give you a few examples as I wind down here of things I have encountered in my work, problems I've encountered, or things I've observed that are very much related to geomorphology. I'm going to talk about red parent material, a little bit more about the Anoka sand plain, calcareous fens again, wetland delineation, just so stories, and wild rice. Red parent material, probably if you've worked in Northeast Minnesota, especially doing wetland delineations, you're familiar with the red parent material, hydric soil indicator. This is indicator F21, and you can mark that as a place where soils are naturally problematic because the matrix of the soil is so red that it can hide normal redoxomorphic features that we use for a multitude of other hydric soil indicators. The occurrence of red parent material isn't restricted to Minnesota, but it's found elsewhere in the Great Lakes region, the upper Midwest, and then in other places in the country. And outside of the glaciated areas, there's going to be different reasons for the occurrence of red parent materials. In our region, the occurrence of red parent materials is the result of the superior lobe of the Wisconsin glaciation. The superior lobe came out of the Lake Superior Basin where it encountered red sandstones, and so it's carrying red parent material. Deposit of those red parent materials that developed into soils with a red matrix. And so that's where we would find red parent materials. And here's a zoom in of our area. So in Minnesota, the superior lobe in Northeast Minnesota. And what's interesting to me when I found this diagram, this actually red parent material extends all the way south into St. Paul, into the Twin Cities, and into Western Wisconsin, just east of the Twin Cities. And I've never encountered red parent material there. My guess is most places it's covered up by Des Moines lobe till, but it could be found in some places. And then the superior lobe is found in different places, northeast Minnesota, and then throughout Wisconsin and Michigan. I have done a delineation on a site this past year where most of the site I did not have red parent material, and then on one end of the site I encountered red parent material. And it was really surprising to me because I didn't realize I was in the area of superior lobe till, but I guess I was. But most of the site, there either superior lobe material was either not present or it was eroded, or it was covered up, and so it wasn't evident. At this one particular part of the site, I did encounter red parent material from the superior lobe. So this is where you would encounter red parent material, and again, it's totally a function of the superior lobe of the Wisconsin glaciation. The Anoka sand plain, I've mentioned that a couple times today. This map shows the location of the Anoka sand plain, broad sandy plain formed by outwash and glacial lakes. Glacial Lake Anoka was in this area. You can find dunes, you can find flats of sand, you can find kettle lakes, tunnel valleys, which are valleys that formed underneath the ice. Although I've never seen one in the field that I recognize as a tunnel valley, so I'm curious if anybody's a geologist and wants to do a field trip to a tunnel valley. I'd love to go along and see it. Mostly flat, general level to rolling. There are inclusions of ground moraine and in moraine, so that's part of the reasons it's not entirely flat. And then it also includes sandy terraces associated with the historic levels of the Mississippi River, especially during the melting of the glaciers that did the Wisconsin glaciation. A cool thing about the Anoka sand plain is there are a lot of plants that are found here that are rare, threatened, or endangered that aren't found elsewhere in the state. And I show a picture of one here, the Xyris torta. And some of the people in this group have done a lot of work on the Anoka sand plain, delineation, mitigation, rare plant surveys. But the rare plants that are there are very much strongly tied to these sandy habitats. A lot of them are found on the margins of sandy lakes, sandy wetlands. Often when there's disturbance, when there's an opening that creates an opening where there's not woody vegetation covering it up, that these plants can be found there. An interesting thing about some of these plants is they are disjunct populations you can find these plants again in sandy areas around the Great Lakes, for instance, in Indiana, and then you can find them again further east on the Atlantic coastal plain. So they thrive on these sandy, flat areas where there's moisture, and they're not found elsewhere in the state or in the region. So it's kind of cool biogeography that there are these disjunct Atlantic coastal plain plants, and it's also cool that there's a lot of unique things that are found just on the Anoka sand plain. As I mentioned, those of you who are wetland delineators probably spend a lot of time on the Anoka sand plain because it's an area of rapid growth. So transmission lines, roads, housing developments, commercial developments, lots of activity on the Anoka sand plain, lots of drainage, lots of sand. And I showed this figure earlier, this sand plain where I was present for a test pit. And this is a drained wetland. So this ditch is actually just found downslope from where this pit was dug. And this wetland was historically a wetland, but it's completely drained. And you can see where the water table is at the bottom of this pit. That's about 8 feet down. And this black soil at the top, that is peat. That was peat that was formed in saturated conditions. It's organic soil, but it is effectively drained because of the ditching and sometimes because of tile lines for agriculture. And this peat can form a granular texture. And so I show a picture here on the lower left of my hand holding this peat, that if you're used to delineating in organic soils and you come across something where it's effectively drained, this peat hasn't been wet, hasn't been saturated for so long that it's oxidizing, it's actually subsiding. And sometimes you can see tree roots that are very exposed because the peat is oxidized, so the soil has subsided and it'll take on this granular texture. And so that's an indication, that's a field indicator that this peat is effectively drained and this is no longer a wetland. So again, this is related to the geomorphology and just something that I've observed in some of my projects over the years. Now, a couple of things about calcareous fens. These are wetlands that are groundwater discharge, and they're pretty rare in the state. There's maybe 100 locations of them. I'm not sure how many, but something in that range, many dozens, probably not more than 200, probably in the range of low 100 number of sites. And what they all have in common as calcareous fens there's groundwater discharge that is coming out of the groundwater that's rich in minerals, and it's probably going through dense till at some place or dense materials, picking up minerals, going through bedrock or calcareous till, picking up minerals. It's low in oxygen, so it becomes super saturated with calcium carbonate, magnesium carbonate, And when and then it's exposed to the ground, to the surface, because it may reach an area where there's exposed, very permeable outwash. And so there's often a piezometric head. So there's an artesian pressure to this that's helping push this water out an area where there is low permeability. And the peatland builds up, and that becomes a calcareous fin. And it's an area of upwelling, as you said, with rich in calcium, magnesium, and other minerals. It's a unique area that has a high diversity of plants that are unique and rare plants that are found in these calcareous fins. The very low oxygen in the water, very high concentration of calcium carbonate. The soils have calcium carbonate deposits. There's low nutrient availability in terms of macronutrients like nitrogen, and the soils is bringing up cold water out of the soil because it's groundwater discharge, very dependent on groundwater discharge. So there are 4 areas in the state where calcareous fins are found: Northwest Minnesota, Southwest Minnesota, Minnesota River Valley, and Southeast Minnesota. And so Northwest Minnesota, where they're found is very much associated with glacial beach ridges at the toe of these glacial beach ridges. And I mentioned that earlier, how they can be found along glacial beach ridges, and there's often can be a conflict between dewatering for aggregate mines and calcareous fins. But they're found, like I said, at the base of these glacial beach ridges where you've got a higher area of glacial till, and then you've got groundwater coming out through these relatively permeable beach ridges with sands and gravels, and rich in minerals, carrying nutrients to the ground, it's groundwater expression. And so you get these peatlands that develop where the calcareous fins form. Southwest Minnesota, you get a similar thing where the discharge is coming through outwash. It's going through infiltration upslope through glacial till, but it's maybe just be coming through outwash rather than a glacial beach ridge. Minnesota River Valley. If you look at this map, if you know the geography of the state and you look at this map, you can see how the distribution of calcareous fins outlines the shape of the Minnesota River Valley, that it proceeds from the western edge of the state southeast and then makes a bend at Mankato and comes up to the Twin Cities. That's the Minnesota River Valley as shown by the distribution of calcareous fins. And I mentioned earlier how Glacial River Warren carved this river valley out, and that exposed or left outwash in many places along the toe of the valley where it intercepted the water table, where the water table now is coming out through this outwash, and calcareous fins occur there. And then southeast Minnesota, that's not going through glacial outwash. If you think back to that karst diagram I showed with the groundwater infiltration through the karst and coming out in the valleys through the seepage, places where you've got the right conditions of minerals and the right amount of seepage to form a seep and a calcareous fin rather than just a spring, you can get a calcareous fin in southeast Minnesota. So in areas, the first 3 areas, the groundwater is infiltrating and percolating through Des Moines lobe calcareous till. And in southeast Minnesota, it's percolating through limestone and dolomite bedrock, in both cases picking up calcium carbonate, becoming mineral rich, where it can be discharged and create a calcareous fin. Again, very strongly related to geomorphology. You don't find that in other parts of the state where there may be groundwater, there may be seepage wetlands, but you don't have the right combination of mineral nutrients and groundwater seepage to form calcareous fins.
There's a question.
Yes.
That you might have already answered, but what is the relationship of calcareous fins in the Minnesota River Valley as it's not a glacial beach ridge?
This slide answers it. This slide will show it. One of the projects I worked on in the past is Seminary Fin. It was a DOT project to evaluate different highway corridors for eventual highway expansion. And some of the proposed highway corridors would have gone near Seminary Fin or through the Seminary Fin, larger Seminary Fin wetland complex. And Fin is in the Minnesota River Valley on the north side of the river, and it straddles Chaska and Chanhassen. And this is a diagram that we prepared as part of the study that we did at Seminary Fin. And I started this when I was at Peters Environmental Consulting, working with Jim Arndt, and Jim prepared this particular diagram. And then I continued my work later when I was at Bar Engineering, and I was working with Ray Willow, who was a groundwater hydrologist. And Jim prepared this diagram that shows the relationship of calcareous fins in the Minnesota River Valley. So you've got Des Moines lobe till on the hillside. You've got bedrock below that. Both of those are calcareous. And then you've got glacial outwash in the river valley. And this is outwash is coarse, it's not very permeable, and it's also calcareous. And so the groundwater that infiltrates and permeates through the till comes out in the outwash in the river valley. And that's where you get the formation of the calcareous fens. So this is why you get a calcareous fen in the Minnesota River Valley instead of the glacial beach ridge. And one thing I did to carry on a little bit further with our impact assessment of we were asking, well, what would happen if they constructed a highway through the fen or through a fen complex? And I prepared this successional diagram to show how you can move from different plant community types based on dewatering or impoundment, increasing the water, decreasing the water, fire exclusion or management, and from fen cover types to non-fen cover types. And I based this both on literature review, the geomorphology, and field observations of impoundment and drainage. So like a seminary fen, there's a railroad embankment that goes through the wetland complex that impounds water. There's tiles, there are drainage ditches. And so that all gave me an idea of how things might change in relation to different types of disturbance. And so I prepared this successional diagram you could predict what would happen if you had impoundment of water and fire suppression or fire management, or use prescribed fire, but you had impoundment, or reduced water with or without fire, or woody vegetation management. This all goes back to geomorphology because it's all predicated on understanding the geomorphology and the groundwater relationship that creates the conditions for a calcareous fen. Okay, a couple examples I want to give from wetland delineations. And I said earlier, wetland delineations just so stories, and I'll explain why I call it a just so story. So a site I did a wetland delineation on had a soil map on the left here, and there were the lower elevations. There was a cutaway loamy sand, and that's the one I mentioned earlier. It's formed in sandy glacial outwash over till, and that sloped. It was relatively flat, but it had a slope to the west. And then at higher elevations on this site, there was nebbish loam, which is a glacial calcareous loamy till. So it was a moraine, probably a ground moraine, probably just dropped underneath the ice when the ice melted and left behind. So not a terminal moraine. And it had an undulating topography. And so you can see on the right, there's a wetland delineation map. And in that area of this nebbish loam, you can see some wetlands that show up that were probably either kettle lakes, kettle wetlands, or they're just a natural temporal low spot in the morainal sediments that were left behind. So in the till that was left, and it's just uneven. It overall had a slope to the west, but it had a lot of ups and downs. And then there's a line of wetlands, and I drew an orange line along here. And this is more or less corresponding with the boundary between these two soil types. And there's a whole series, about 10 different wetlands that were all seepage wetlands that occurred along this line. And so once I understood this and started delineating, I came up with a hypothesis to explain why I'm seeing all these wetlands here in relationship to the soil series descriptions and the geomorphology. And I'll show you this. And this is what I call my just so story. I don't want to say it's just wild speculation. Let me say it's an untested hypothesis, which is kind of another term for wild speculation. But what I think is happening here is there was till on top of sandy outwash that had a slope with sandy outwashes on top of more till, and where I would see the series of 10 seepage wetlands occurred right here along the boundary between these two soil types. And it was interesting because, like I said, there were about 10 different polygons of seepage wetlands. There was no other source than groundwater seepage to them. It was interesting to me how there's so many of them just kept repeating along this hill slope. So this is my just so story that I think there was where there was this exposure of this very permeable sandy outwash. It was carrying groundwater laterally and bringing it out to the surface and form these wetlands. Another example on this site from wetland delineation was an area that was mapped as Dalbo silt loam and Taylor silt loam, a complex of these two, or Taylor silty clay, a complex of these two soil series. And they're moderately well or somewhat poorly drained soils, and they're formed in clayey glacial lacustrine sediments on lake plains or moraines. And it said in the soil series said they had slopes that range from 0 to 45%. a 45% slope is not consistent with a glacial lake plain in my mind. That's a lot of slope. Glacial lake plains in my mind are pretty flat. And then this site has a plateau, so I drew a cross section across this here on in the aerial photograph, and this cross section I represent with this profile view on the lower right. So there were low areas on either side, and it was a plateau that tapered off on either side. On either side, there were conifer swamps. And in the top on this plateau, there is this undulating mosaic of microtopography of wetlands and uplands. And this slope on the sides and the microtopography, this undulating microtopography, weren't consistent in my mind with the lake plain. So I created another Just So story to explain why this might be happening. And here's my interpretation, my untested hypothesis that I thought that maybe there was glacial till that might have had a block of ice on top of it, and a glacial lake formed on top of that, and the glacial or the lacustrine sediments settled out on top of the ice. And I was thinking about later after I made this diagram that maybe that block of ice doesn't even have to be there. Maybe it was just a glacial lake that formed on top of the till, and there's lacustrine sediments on that. Either rate, once the glacial lake was gone, once the hypothetical ice was gone, you've got this blanket of lacustrine sediment that settled out on the till. So the till would account for why you've got this undulating topography, and it would also account for why you've got these slopes, because glacial till can be flat to very sloping, however the glacier left it. And then you had this undulating topography on top, and I used the mosaic problem area method of delineating where I did line transects, because these microdepressions were just so difficult to delineate that I just decided I had to use the problem area approach to how I delineated that one. So again, this is a problem area. It was a little bit challenging at first, but I came up with an explanation, a way to approach it with a delineation, and I came up with a hypothesis to explain why it is the way it is based on a geomorphic interpretation. And I admit I didn't go out and do a lot of deep boreholes to determine if my hypothesis is correct, but for me, it helped make sense of it. Just having a hypothesis or being able to propose a way that you could find a site in this condition helps me in a delineation. I had this mosaic of wetlands at a higher level than the surrounding conifer swamps. Well, if they're sitting on a little plateau of till, that makes sense, because that till can have a lot of clay, very low permeability, poor drainage, microtopography from the undulating till. Okay, that all makes sense. So that's how I interpreted that site. One other example I want to share related to geomorphology, and this is plant biogeography. Project I worked on at one point, we were looking at the distribution of wild rice in the St. Louis River watershed. And in the eastern portion of the Iron Range, there's a lot of wild rice found in the St. Louis watershed and in the tributaries to the St. Louis River of the Embarrass River and the Partridge River. And once you get below the city of Aurora, there's no wild rice all the way down to Duluth. And once you get to Duluth, as you get downstream of Cloquet, so I don't know, some 100 miles, river miles, something in that range, a lot of river. There's no wild rice until you get down to the flat area in the estuary behind the Duluth Harbor. There's wild rice there again. So the question is, why is there no wild rice in the central portion of the river? There is in the estuary. That makes sense because that's flat, really associated with Lake Superior. And then it's also found wild rice is found in the upper reaches of the St. Louis River Valley. Well, a group of us puzzled on this. This is a team at Bar Engineering. We puzzled on this, and then we superimposed geomorphology on this, and we went back to the ecological classification system, and we took this layer, this GIS layer, and this is land type association. So earlier I talked about sections, provinces, sections, and subsections. So this is the next layer below that in the hierarchy. These are land type associations. And when we made a map of wild rice distribution that we know from these forests and lakes, or these rivers and lakes, in relation to these land type associations, we found out that wild rice is present on glacial till land type associations, in particular the Big Bird Lake Moraine, the Aurora Till Plain, and the Toimi Drumlin Plain. When the St. Louis River passed into lake plain land type associations, particularly the Squagma Lake Plain and the Warble Lake Plain, wild rice was no longer present. Well, to me, this was not a random occurrence. There had to be a deterministic factor based on the geomorphology, and what we proposed was that in the upper reaches where the river is going through these morainal till landscapes, there are rock outcrops that create pools. And you can see in this aerial photo on the upper left, the river has very broad curves, very winding, or very broad winding curves, I should say. And there are pools, and the pools act effectively as lakes. And then there are rock outcrops that create riffles that separate the one pool from another as the river descends. So there's low water velocity and there's minimal water level variation because you've got these repeated rock outcrops that act as small check dams that put a check on water velocity and water level variation. And wild rice is an annual grass that reseeds itself every year. And so if it experiences too high of water levels, it will drown out, or if it has high water velocity, it can't remain rooted and wash away. Well, on the lake plains, you can see this river, the aerial photo of the river is much more sinuous. Those curves of the river are much tighter, and it's going through a sandy substrate, and there are no rock outcrops. There are no constraints on water velocity or water level variation, so you can get a lot of fluctuation in water level over the course of the year, enough that you might be able to drown out the wild rice, and the water velocity is unrestrained. So in a high water event, there's nothing to slow that water down so it could wash the wild rice away. So that's what we hypothesized was the explanation, a geomorphic explanation to explain the biogeography of wild rice in the St. Louis River watershed. So I thought that was kind of a cool finding. So to summarize, geomorphology, in my mind, is important to wetland scientists because it helps us understand the occurrence of wetlands and wetland types. As I said a couple of times, they're not random. The occurrence of wetlands and wetland types, they're not random. There's a certain amount of randomness in terms of where the glacier sediments were deposited, but in terms of the formative processes that result from those parent materials, there are deterministic factors that result in a prairie pothole region that result in regions where you find calcareous fens and where you don't find calcareous fens and that kind of thing. Geomorphology is important to understand wetland ecology, native plant communities, plant biogeography can help inform impact assessment, and it can also help inform or help figure out problem areas in wetland delineations. So I'll come back to my original, what I started with, Bert Barnes, the University of Michigan, singing the song from The Music Man. And if you haven't seen The Music Man, you can still, I think it might be still playing at Chanhassen Dinner Theater. This really struck a chord with me because when I was 11 years old, I was in a production of The Music Man. If you've seen The Music Man, you know Winthrop Peru, who sang Gary, Indiana, Gary. That was me when I was 11 years old. So I've always been kind of a nerd for The Music Man. And the opening song, You Gotta Know the Territory. Well, as it turns out, my brother was the one in that production some 40 years ago or whatever it was of The Music Man. As my brother was saying, you got to know the territory. And so Bert Barnes reminded me of that. And I remind you, geomorphology, you got to know the territory. It helps understand a lot in wetland science. So thank you for your attention. I'd be happy to entertain any other questions.
And thank you so much. That was a really interesting talk. Another question then. Would you say that most wetlands in Minnesota are formed by glaciers?
Yeah, I got to think about that. Yeah, I think so.
Most of
Pardon me?
Oh, it just sound like there's just so many different ways that glaciers cause wetlands. So it's like, wow, that sounds like a lot of majority of wetlands would be formed by glaciers here.
Yeah, by far the vast majority of the state is glaciated during the Wisconsin glaciation. And so that parent material is forming the wetlands. In the driftless region, they're not glacier created wetlands, but in the rest of the state they are, except, where you have alluvial valleys. And so those are, more recent working of, within the last 10,000 years till last year, all the alluvial sediments are being reworked in the floodplain valleys.
There's a question in the comments. Any idea why the driftless never became glaciated?
That's a good question. I've never heard any geologist explain why that is. I think it might just be random chance. But I've never heard a geologist. I've heard a few geologists speak about the driftless region. I've never heard them address this question. I've never heard them offer an explanation of why the driftless region was missed. So I don't know. There's no mountain range or anything like that diverted glaciers on either side. So I think it's random chance. If anybody has a different explanation, I'd love to hear it.
And thank you so much for presenting. And me personally, the topic I've been very much wanting to know, so I very much appreciated this.
No, you're welcome. Yeah, like I said, it's been very interesting to me ever since I took that forest ecology class. So it's been a little hobby horse of mine to learn more about glacial geomorphology.